Hello everybody, I'm Captain MAMGAIN. Last we had discussed about uh, effect of discharging, loading and shifting of weights on the center of gravity. Today let us see how density affects a vessel. Now this is something just a recap on what you already know, mass density. And when you're taking all the units in MKS system, the density is measured in kg meter cube. And mass is volume into density, and you can see when you're doing it in MK system, the final answer of mass is kgs because meter cube gets cancelled here. Relative density is the ratio. Freshwater density, which we are taking as 1000, and here again you will see that relative density does not have any units. Now relative density is multiplied by 1000 to give me the density, or density relative density is density divided by 1000. Mass volume into density in MKS system, as I said, we get kgs. Now instead of density, if I just replace density with relative density, so I'm just multiplying the kgs with 1000, so it becomes 10. So when you're calculating with relative density, your answers are in tons, and when you're doing it with density, it is in kgs. This is something what you got to know. Now when a body floats at rest in water, Archimedes said it must displace its own weight of water. And this is what we'll be seeing here. Let us say that this is a homogeneous box weighing 1000 kgs with the dimensions given here. And center of gravity, as we talked last time, lies somewhere for a homogeneous body, lies in the center of the body here. If it is to float in water, which I have taken the relative density as of salt water, 1025, it is going to displace the mass of water. What will be displaced will be equal to the weight of the body itself. And the amount of depth which is below the water, we refer to it as drafts. The mass of water displaced is volume into density, and the mass of water what is displaced is also the weight of the box, what we are talking about here. So the volume of water displaced, length, breadth, and the draft into the density is 1000. And when we work it out, we come to know that the draft here is 0.244. Now, if the same body was to float in freshwater density 1000, it will come to some draft here d2. The mass of water displaced again is going to be the same as the weight of the body itself. And when we work it out with length and breadth and the depth, figure out that the draft has come out to 0.25. So we notice that there is a change of draft when a vessel goes from one density, from water of one density to a water of another density. So effect of density, if the weights are constant, as you can see here, there is going to be a change of draft when the ship moves from water of one density to the water of another density. Now I'll just refer to this as old density rather than salt water and fresh water here, old density and new density that this ship is going from here to here. Now, what is the effect of density and the displacement is constant for box-shaped vessel? Now you can see that the drafts have changed, as we saw earlier. I calculated it. Draft has changed, so underwater volume must have changed in both the cases. And as you can see in the figure, that there's a difference in underwater volume here. But the displacement of water, weight, mass, is equal to the weight of the body itself in both the cases. So mass of water displaced when it was in the old density and the mass of water displaced in the new density, they are both equal. And to calculate, we use the formula volume into density. So underwater volume, old underwater volume, and new underwater volume multiplied by the respective density, they both should be equal. And volume is length, breadth, depth. Length and breadth are the constant in both the cases. So we come to the conclusion of old draft divided by new draft is equal to new density by old density. So when the ship goes from one ship to another, not a ship, uh, talking about a box ship vessel here, this formula holds good. So you can find out what is going to be the change in draft by this formula here. This is applicable for box shape vessel, not for a ship, because ship is not a perfect geometrical shape, in which we'll be talking about freshwater allowance, which we'll be talking about in some other topic later on. Now let me just consider that in both the cases, that's old density and new density, the drafts are the same. So I just brought in the ship with same drafts here. So in this case, underwater volume in both the cases would be the same, because length, breadth, and depth are the same. So underwater volume would be the same in both the cases. Now, underwater volume here is length into breadth into whatever the draft is. And if you multiply it with the density, then you'll get the weight. And to float, it has to displace the same amount of water. What is the weight of the box here? So mass of water displaced is equal to weight of the body itself, which is volume into density, what we got here. And we figure it out, that the weight would be 976 kgs upon 976 tons. So we see that when a vessel, or when a box is shaped vessel, which is shown here, is taken from one density to another, and the drafts are still the constant. Something has changed, and what has changed is the displacement. So that means you must have discharged something, used something. So now your drafts are the same. So if you go from one density to another and the drafts are same, then displacement has to change. So two things what we saw: one was the drafts are changing, or displacement is changing when you are moving from one density to another. Buoyancy, everybody knows about buoyancy, but anyway, just a recap on buoyancy. To float, as I said, same mass, same weight of water is being displaced. Now, there should be some force which is holding on this particular ship at rest. That is not going down any further, it's not going up. So there will be some force which is pushing it up, which is equivalent to the weight of the body itself. And this force is what we refer to as force of buoyancy. The force of buoyancy acts vertically upwards through a point which we call center of buoyancy. And center of buoyancy is the center of gravity of underwater volume. So in this particular case, when you look at it as a homogeneous box here, it will be right in the geometrical center of underwater volume. So that will be half the draft, whatever we have achieved. Now this submerged portion is the one which is giving me the buoyancy. The enclosed space above this are being held in reserve. They are not providing me any buoyancy at present. They are being held in reserve. If any extra load is going to be put on to this vessel, that is the time this extra space, the space above the water line, would give me the buoyancy, and this is what we call as reserve buoyancy. Now let me just add some weight here. You can see here weight. So as soon as the weight is added up, the ship will move down. With, of course, center of gravity again changing according to the weight and buoyancy according to the underwater volume, and it will come to balance again. This is what is reserve buoyancy, what was there on top, and reserve buoyancy is the volume of enclosed space above the waterline. Taken as percentage. For a vessel to be upright, I'm talking about it's upright, there is no list or anything like this. The center of buoyancy should be vertically below the center of gravity. Where the buoyancy is and gravity is, we'll talk in detail once we talk about list strings and other things. But as for now, if the body is going to be upright, then B should be vertically below G. Few terms what we use here is light ship. Light ship is the weight of the ship, which is when it is absolutely empty. When it comes out of the yard, you're given what is the light ship with bare minimum things like I said, boiler water, lube oil, cooling water, etc. is there. So that is the weight of the ship when it is fully empty. Then we talk about dead weight. Dead weight is the maximum weight what the ship can carry. That will include everything: your crew, your provision, your oil, water, whatever it is there, the whole weight, whatever maximum we can load to a particular draft, which we'll be discussing a bit later. But here it will suffice that dead weight is the maximum weight the ship can load. And displacement is the volume of water what it is displacing at a particular draft. So as the draft will change, it will all depend. Your displacement will keep on changing, and the maximum would be when it is loaded fully. This is one term what we'll be using quite often once we start doing some tons per centimeter immersion. So tons per centimeter immersion is the amount of tons what are required to increase or decrease the draft by 1 centimeter. You load, you increase, you discharge, you decrease the draft by 1 centimeter. Now let me just have a look here. The ship, this is the water line, this is your keel, this is your draft here. Let me add X tons, which would increase the draft by 1 centimeter, and that is what we will be calling as the TPC. Once I added it up, it will sink and the draft would increase by 1 centimeter. Now, whatever this weight has displaced certain amount of water, which is equivalent to the weight what we have added to this. And when we talk about masses, we are talking about, when we talk about weight, is volume into density. Now, the volume is what? Length, breadth, and 1 centimeter, because it is increasing by 1 centimeter into density of water. So this is the mass that would be required to immerse the ship by 1 centimeter. Now length into breadth is the area. I've just converted this into meters here, 1 by 100, and relative density. So I'll get the answer in tons here. Here I was getting the answer in kgs. Now, when you talk about a ship is not a rectangle or a square. It's got a shape something like this. So I cannot get the area length into breadth. So on the ships, when we talk about ships, we talk about water plane area. What is the water plane area at a particular draft here? So the formula for TPC just changes over to water plane area instead of just plane area here for ships with relative density divided by 100. So TPC salt water is water plane area of the ship on a particular draft multiplied by its relative density divided by 1. If you look at this formula here, the TPC is got involvement of salt water, I mean the specific gravity or density here. So depending upon what uh, density water you are sailing on, your TPC should also vary. Now let's say that the ship is sailing on a dock water of relative density dW here. If I just cross multiply here, I get water plane area is equal to TPC of salt water multiplied by 100 divided by the density, relative density of salt water. Now, if a ship is sailing at the same draft in a density, some other density here, that's your dock water density, it's got the same draft, so your water plane area will be the same. The TPC of dock water multiplied by this density of dock water is going to be the water plane area here in this case. If you equate both of them, 1 and 2, you get this. And that works out to TPC dock water divided by TPC salt water relative density. So when you are going from one density to another, the TPC would change in proportion to this particular formula here. So effect of change of density, what we have seen today is displacement was constant, there was change in draft. When if the draft was constant, that means there was a change in displacement. And now we saw that there is a change in TPC. Now you see all the hydrostatic particulars of a ship are given in salt water. The drafts are in salt water, you are in some other displacement. So your displacement would have to be changed, as we saw that for 2.8, same draft, the displacement would be different. And similarly, we saw that TPC also would be different. We'll talk about rest of the changes in the next lecture, but this is going to be my topic in navigation next. It's going to be about position lines. So you'll be able to get an idea about what position lines are all about. Thank you for watching. I'll be continuing stability topics on freshwater and aquatic allowance. Till then,